Good afternoon, everyone. My name is Will Roberts, and I'm here to present the results of some experiments that we've been doing in Berlin to compare selectional preference models on the task of automatic verb classification. So I'd like to start out with giving some definitions and making clear some assumptions that we make in this work, showing you our evaluation paradigm, and then I'll move on and introduce the models that we compare and present some results and discussion at the end. So selectional preferences is the idea that a predicate can select for its arguments in some way. We have here an example, my aunt is a bachelor, and this sounds odd, presumably because there's something about the meaning of the predicate bachelor that doesn't agree with its argument aunt. In this work, the predicates that we're interested in looking at are verbs, and what we'll want to do is to model verb arguments empirically. So for instance, we might be interested in recording that bread is a more likely argument to the verb eat than newspaper. We're then going to compare different selectional preference models by evaluating them on an automatic verb classification task. And by this I mean an unsupervised clustering task where we try to sort verbs into classes that have related meanings. On this task we use a baseline that makes use of syntactic features to describe verb behavior, namely subcategorization. And I'm going to come back to subcategorization in a few minutes. We're then going to add the information from the selectional preference models on top of this baseline and look at the effect of this addition. Okay, so our work is done in German, and we have here an example sentence which I've translated as, "We will not use your survey responses for private purposes." And for the selectional preference modeling, we're going to want to record the arguments to the verb use here. We take the heads of arguments and we lemmatize them. So we're going to record that use has a direct object, which is survey datum, and it also has a prepositional phrase, which is headed by for, and the argument to the PP is purpose. We also include other kinds of grammatical relations. So we include subjects, and in this example, the subject is the pronoun we, and we don't handle pronouns in this work, so we ignore that. And we handle datives as well, but that's not shown in this example. Okay, I'm going to define a selectional preference model in a non-standard way as a function that maps nouns onto a concept label. Okay, so for instance, an example might be that a noun that's the direct object of the verb eat might be mapped onto the label food. This is a schematic where on the left side I'm putting the baseline method, which I said uses only subcategorization information. And I'd like to put it to you that this is a kind of selectional preferences model in the sense that I've just introduced, because it maps all nouns onto the same null concept. So in essence, we're capturing no selectional preference information. On the right side, I'd like to introduce a really simple model, which I'll call lexical preferences. And in this model, every noun is mapped onto its own concept label. In principle, there's any number of ways of mapping nouns onto concept labels. And this graph is trying to indicate that the idea of granularity here. So we might have fewer concepts or more concepts. And this granularity is a parameter that we set out to investigate in this work. So our primary hypothesis for this work is that the best performance on the automatic verb classification task, that we're going to find that using some kind of selectional preferences model that has generalization over nouns. In other words, a model with some intermediate granularity. And we hypothesize that such a model will do better than our baseline on the left and better than this lexical preferences model on the right. So I promised to talk about subcategorization, which I said is used for our baseline method. And I'm going to say a subcategorization frame is a particular combination of syntactic argument types that a verb instance can co-occur with. In our example sentence here, the verb use has a subject, a direct object, and a prepositional phrase. And we can encode this combination with a tag that shows these three argument types. So particular verbs like to show up with some subcategorization frames and not with others. And if we had a description of the subcategorization frames that a verb likes to some subcategorization preferences. Subcategorization is the starting point for this work because of the theory of Beth Levin that the semantics of a verb can at least partially determine its syntactic behavior. So here is a high-level overview of our pipeline. I'm getting ahead of myself. That we use in this work. So on the left side, we start with this corpus, which is text from Google searches, so text in the wild, which we then automatically parse with a dependency parser that gives us part-of-speech morphology and lemmatization information. At this point, we run a tool that we've developed, which takes every verb instance in the parser output and assigns it a subcategorization frame tag, like we've seen on the previous slide. So this gives us something that we call the test set. And in the majority of the work that I'm going to talk about today, the test set uses about a quarter of this corpus. So it contains 3 million verb instances that are all tagged for subcategorization information. It's this test set that we're going to then enrich with selectional preferences information. So once this, when we have this test set, then we take the verbs in the test set and we cluster them using hierarchical clustering with Ward's criterion, which is a standard deterministic algorithm. And this produces a verb clustering that we can then compare to a gold standard. And the standard that we use in this work is one that was published by Schulte and Walde in 2006, and you can think of it as sort of a small-scale VerbNet-like classification. The statistic that we use for evaluation is called the pairwise F-score. Okay, so the way that the clustering works in these studies, we build a vector for each verb, and each vector position records a count of the number of instances of that verb that occur in a particular subcategorization frame. Okay, so in our corpus, we observe 673 different subcategorization frame tags. So these vectors are 673 dimensions long. We can normalize these vectors, like I've tried to indicate here, to give a discrete probability distribution, which you can think of as an empirical estimate of the verb's subcategorization preferences. And then we just define the dissimilarity between any two verbs to be the Jensen-Shannon divergence between these probability distributions. The Jensen-Shannon is a sort of symmetric version of the Kullback-Leibler divergence. So it's an information theoretic metric on probability distributions. Okay, so that's our pipeline, sort of sketched. And now I'm going to go on and talk about models, starting with the most simple one, which is the lexical preferences model that I've already shown on this schematic a few minutes ago. As you can see, it ends up being sort of a lexicalized subcategorization frame. So we just take the arguments to the verb and we tack them onto the end of this subcategorization frame tag. You'll note that the subject is missing here because, as I mentioned before, it's a pronoun and we don't handle pronouns. So the effect of this procedure is that the number of subcategorization frame tags that we use is going to be increased. So we're not going to have 673 dimensional verb vectors, but we're going to have thousands or tens of thousands of dimensions. So the verb vectors are going to get longer and presumably also sparser. And to control for sparsity, we have a parameter that we call n, which we use for all models in this work. And it is the number of nouns that are included in the selectional preferences model. We use a ranked list of the most frequent nouns in our corpus. And then the idea is if you observe a noun argument to a verb and the noun argument has a rank that's greater than n, then you chuck it out. You ignore it. Okay, the next model I want to show is one that was described by Sun and Korhonen in 2009 and successfully used for automatic verb classification. And the crux of this is that it uses a partition of nouns. And the nice thing for me today is that this is identical to the procedure that we use for verb clustering. So briefly, we build a vector for each noun where each position in the vector is a count of the number of times that noun shows up in a particular grammatical relation to a particular verb. And these vectors are around 11,000 dimensions long. Then, like before, we normalize this to a discrete probability distribution. We define dissimilarity between nouns to be the Jensen-Shannon divergence between their probability distributions. We use hierarchical clustering with Ward's criterion. And this gives us a partition of n nouns into m classes. Okay? So we're using the parameter m here as a way to model granularity. Once we have this partition, the selectional preferences function is just an equivalence relation, such that any two nouns that are in the same concept class will be assigned the same label by the function. Okay. This model, the third, also uses a noun partition. in the same way as before. I build it differently. So this noun partition is built using a word space model. And word space models are sort of a standard technique in computational linguistics these days. So I'm not going to go into detail about the exact parameters of this, except to say that we use sentences as windows for this word space model. And we use a technique called context selection that zeroes out infrequent features. The result of this is going to be, again, that each noun has an associated vector. And then we can use the cosine similarity to judge the similarity of any two nouns. We feed this similarity information into a spectral clustering algorithm. And again, we arrive at a partition of n nouns into m classes. So we have two parameters of this model, n and m, which are the same as the sun model that I just showed. Okay, the fourth model does not automatically induce a selectional preferences model, but rather it uses a manual resource, namely GermanNet, which is the German edition of WordNet. And WordNet-based selectional preference models have been used a lot in the past, partly because they give you an inventory of nouns to look at, and partly because the noun ontology allows you to generalize concepts in an easy way. Because we're interested in looking at granularity, we do this in a really simple way by defining a parameter we call depth, which is the number of hypernym links that connect a synset to the root node in the noun hierarchy. And then using depth, we create a target set, which you can see here in red, which is the set of all synsets that are at or less than depth in the hierarchy. So then a noun can be mapped onto a concept label, or synset, in the following way. We look up all of the senses of the noun. So there's here two for the German word for year. And then for each sense, we just track up its hypernym chain until we hit something in the target set. So in essence, each sense of a noun can vote for something in the target set. And the result of this is that, unlike the models we've looked at so far, this produces a soft clustering of nouns, or rather, every noun can belong to more than one concept. Okay? What this means is that every verb instance in our test set can contribute fractional counts to more than one subcategorization frame tag. That's cool. Okay, so the parameter here is depth. It doesn't include the n parameter. I lied earlier for brevity. Okay, last one. Last one is latent Dirichlet allocation. This is often used for topic modeling, except here, instead of modeling words in documents, we're going to model nouns in verb grammatical relation pairs. So we use the same data that we used to build the Sun-Korhonen model, and we feed it to an off-the-shelf tool called Mallet. And what this gives us when it builds its model is for each verb grammatical relation pair, we get a distribution phi over concepts. And every concept z then has a distribution theta over the n nouns that are included in the model. Again, we use the parameter m to model granularity. And here we set m to be either 50 or 100. So like the GermanNet model, with this, nouns can belong to more than one concept. And we originally thought this might be useful for modeling polysemy in nouns. As it turns out, it isn't. So we also have a way to convert this into a hard clustering, wherein every noun just maps to its most likely concept, if that makes sense. Okay, so I've now introduced 5 models, and each of them has one or more parameters. We basically did a grid search over the values these parameters can take, and this table is summarizing our results with the best parameters for each model. So on the right side, you'll see the F score that indicates performance on the automatic verb classification task, where higher numbers are better. And there's 2 things we can say right off the bat here. One is that all of the models that we compare do better than our baseline, so that's quite promising. And the second is that our hypothesis is confirmed. You'll remember we said that models of intermediate granularity should outperform the baseline and the lexical preferences. And here there are 2. The Sun-Korhonen does so, and the hard clustering LDA model does so. Okay, so to get into a bit more detail, the GermanNet model doesn't do particularly well. It gets its best performance with a relatively large value of depth, so ends up being fairly fine-grained. The hard clustering version of LDA does better than the soft clustering LDA. We were surprised by that. LDA does quite well. Both the hard and soft versions are optimized with 50 topics instead of 100, so they end up being the most coarse-grained models on this slide. The best model that we looked at was the Sun-Korhonen model. It's quite fine-grained with an average of 10 nouns per class. And it picks its value of n to be 10,000, which is the largest value of n that we allowed it to pick. So it's trying to maximize its coverage over the test set. The word space model doesn't do as well as the Sun model, but also tries to get as wide coverage as it can over the test set. And at around 20 nouns per class, it's also a fairly fine-grained selectional preferences model. The lexical preferences model is third on this list, which we think is quite good because it's a very simple model, and it's significantly better than our baseline. All you need to get this to work is to tune the parameter n for data sparsity, which I can show here. So here the black line is the performance of the lexical preferences model on the automatic verb classification task, and the gray is showing coverage of our test set data. So you can see as you increase n, the coverage of the test set data goes up, and the verb classification performance also goes up and then starts to fall again, presumably as sparsity becomes a problem. Okay, we had two methods that rely on a partition of nouns, and we can say some interesting things sort of qualitatively by looking at the classes of nouns that they induce. The first is the Sun model, which uses syntagmatic information to induce its noun classes. So we're interested in which grammatical context a noun appears in. And the word space model uses paradigmatic information, right? So we're interested in which sentence context a noun appears in. And this goes some way towards explaining the next finding, which is that if you look at the classes that Sun induces, you find that they group together synonyms and cohyponyms. So because it's quite a fine-grained model, we get these small classes which are semantically quite consistent. In contrast, the word space model groups things together thematically. And the classes in the word space model can often conflate semantic roles. So you'll get nouns that denote professions, and they'll be classed together with nouns denoting locations where those professions are carried out at. Okay? We think this is probably slightly unhelpful for selectional preference modeling. Another thing you can do is look at the statistical distribution of the noun classes. In Sun, we find that the classes have relatively uniform size, and we can quantify this with the variance in class size, which comes to a value of 37. In the word space model, there's many singleton classes, and there's a few very large classes, the largest of which covers something like 14% of the test set. So it's very big. The class size variance here is much larger at 2,800. In the large classes in the word space model, we find that the nouns are not semantically related to each other at all. So all of this sounds kind of bad for the word space model, and it raises the question of how it outperforms the baseline at all. And we suspect that the large classes neither help nor hurt performance. The small classes are too small to hurt. And in between, there's classes which are granted grouped thematically, but are probably still helpful for what we want to do. We find classes that group proper names together so that you get diseases classed together or country names classed together. Okay, one last result. We wanted to look at the effect of the test set size on this task. So we're comparing the best models here. The 3 million verb instances that we had are somewhere around the middle of this, and on the right there's the full corpus size. On the left you can see that sparsity is a problem, and the baseline, which is the solid black line, does best. But as we increase the test set size, selectional preferences start to offer improvement. The lexical preferences model is quite competitive. That's the black dashed line. And I will just skip to conclusions now. So the first is that all of the models that we looked at are useful for automatic verb classification. The second is that we wanted to investigate this concept granularity parameter. And we find that with the possible exception of the LDA model, all of the models that we look at seem to like to be quite fine-grained. In particular, lexical preferences does quite well if it's tuned for coverage. And we think that a selectional preferences model is advised to have these classifications of proper names. So given names grouped together, corporation names grouped together, and medications grouped together, that kind of thing. Finally, based on the performance of the Sun model and the LDA model, we would advise you, if you're inducing your own selectional preferences model, to rely on syntagmatic information rather than paradigmatic. And that's basically what I've got to say today. So I'd like to thank you for your attention and ask if anybody has any questions now. Thanks.
About the word similarity model, another difference from the SUN model is that it uses spectral clustering.
That's right. So partly I can motivate that by saying that the cosine similarity gives us a similarity metric instead of a dissimilarity metric, like with the Jensen-Shannon. The other part of that is I tried both hierarchical and spectral clustering worked better for that. So I'm leaving some details out here, yeah, we did try hierarchical clustering. I tried spectral clustering with the SUN as well, and hierarchical was better.
Mm-hmm. So the difference is due to the space, the actual features that they use rather than the clustering. The reason that word similarity model performed worse is not due to the clustering.
I see. This was consistent. It didn't matter which kind of clustering I did. Word space model was worse than SUN. That's right.
So one more question I had is, there are issues with sparsity as you increase the number of words or classes, and you start to see more coverage of the data, but it might not always help. So I was wondering if you, in some of those models, if you do have to leave some data out, like there is no coverage of that data because n is not large enough. Have you tried instead of leaving them out to use the backup?
Yeah, that's a very good idea. No, we didn't do that. So the idea is you're going to see sparsity strongest with the lexical preferences model because it's a one-to-one between the number of nouns and the number of concepts. In the other ones, because nouns are classed together, you'll be able to generalize a little bit over data. Still, we saw, for instance, with the LDA, we built quite large models that had very large values of n, and they would still suffer from sparsity as n increased. So the way that we did it here is relatively simple. Using a back-off would be a nice way to handle it in practice, I think. But I was just sort of interested in a side-by-side juxtaposition of these different methods on a single task. So I kept things simple to try and just compare apples to apples. Yeah, but it's a good idea. Thank you. Okay.